Hi friends, this is our second video on the topic of complex number for IIT JEE part 1. This is second video of part 1 lecture, and you can see the notes of these lecture along with the copy of this video at Exxamm.com/12389. In this lecture we will cover rotation of complex number, de Moivre's theorem, or as it should be rightly said, de Moivre's theorem, and then we use that theorem to calculate the cube roots of unity and then nth roots of unity. Then we will expand on the concept of geometrical representation of a complex number, and then we will do loads and loads of examples on these topics. Okay, to develop the general concept of rotation of complex number, let us take two complex numbers z dash and z such that the angle between z dash and z, the difference between the arguments of these two complex number is alpha. That if z is rotated by an angle alpha in counterclockwise direction, it will somehow merge here, or if the modulus of z dash is greater than modulus of z, then it would be an extension of OZ, but it would lie on the line or joining OZ. So now the argument of OZ dash is theta dash, and argument of OZ is theta, and the difference between theta minus theta dash is alpha, and we have to find the relationship between the complex numbers z and z dash. Okay, let us say what is the value of z upon z dash. Now z is equal to modulus of z e to the power I theta, that is this angle, because that is the argument of z, and modulus z is the modulus of z. And similarly z dash is equal to modulus of z dash e to the power I theta dash, because theta dash is the argument of z dash. So we have just substituted the value of z and z dash here, nothing new. But what is the, if we can also write it as modulus of z upon modulus of z dash e to the power I theta minus theta dash, that is equal to e to the power I alpha, because as is obvious from this diagram and by definition, theta minus theta dash has been defined to be equal to alpha. This was a simple case. Now what if there are 3 points? Now in this case, the 3 points are z1, z2 and z3, and we are, rather than rotating z2 OZ2, we are rotating z2 z1, this line AB by an angle alpha, and so that it is lying along the AC here, AC. Now we have to find the relationship between Z3, Z2 and Z1. Now if we transfer these 2 points B and C to P and Q in such a way that OP is equal to AB in length, and it is parallel to AB. So this is, we have just kind of dragged this line here, and similarly we have dragged this line AC here. So Z3, now this has become and A has shifted to O. So we have taken this particular triangle and have dragged it like this to this particular point to origin. So in this case, what are the revised coordinates of P? What are the coordinates of P and Q? P would be our Z2 minus Z1, because this was the length, Z2 minus Z1 was the length of AB, and Z3 minus Z1 was the length of AC. We have already done these calculations in the representation of complex number in Argand plane. So the point P would be Z2 minus Z1, and point Q would be Z3 minus Z1. It is akin to saying that we have shifted origin to point A. In that case also, and by the analogy of shifting of origin and applying it in the context of complex number, we can very easily understand that this Z2 minus 1 and Z3 minus Z1 are the coordinates of point P and Q. This is origin, and this would be the angle alpha, that is the angle between these two. Now applying this particular formula, that Z upon Z dash, where Z dash is Z2 minus Z1, Z is Z3 minus Z1, we will get that Z3 minus Z1 upon Z2 minus Z1 is equal to our OQ upon OP, that is modulus of Z3 minus Z1 upon modulus of Z2 minus Z1 e to the power I alpha, that is cos alpha plus I sin alpha. So the final run में the equation on the basis of rotation of complex number becomes Z3 minus Z alpha upon Z2 minus Z alpha is equal to Z3 minus Z alpha modulus upon Z2 minus Z alpha modulus multiplied by e to the power I alpha. Now we will do an example of this rotation of complex number, which will make our concept more clear. I can spend more time explaining this thing again and again, but it would be much easier for you to understand this thing from the example. As of now, I just suggest you remember these two formulas, that Z upon Z dash is equal to modulus of Z upon Z dash e to the power I alpha, where alpha is the angle when we rotate the Z dash in counterclockwise direction on the base along the origin. And here, if we rotate Z2 with respect to Z1 to Z3 with by an angle alpha in counterclockwise direction, then the relation is Z3 minus Z1 upon Z2 minus Z1 is equal to modulus of Z3 minus Z1 divided by modulus of Z2 minus Z1 is equal to e to the power I alpha. Now this is a very simple but very good example to explain the concept of rotation of complex number. Now let us see that let us check the question. Consider a square ABCD such that Z1, Z2, Z3, Z4 represent its vertices A, B, C and D as shown in this. This particular point is C, and Z1, Z2, Z3, Z4 in counterclockwise direction. Now we have to express Z3 and Z4 in terms of Z1 and Z2. So let us do it like this, that let us say that Z1 when rotated counterclockwise by an angle pi by 4, the whole angle is pi by 2, this angle is pi by 4, so it would become it will lie on the line joining A and C. Now what would be the when we apply the rotation theorem, what would we get? We will get Z3 minus Z1 upon Z2 minus Z1 is equal to modulus of Z3 minus Z1 divided by modulus of Z2 minus Z1 into e to the power I alpha. Alpha in this case is pi by 4. So this is our equation, Z3 minus Z1 upon Z2 minus Z1, and we have just used the rotation of complex number formula when we have rotated Z2 by an angle of pi by 4 in counterclockwise direction. Now if we what is e to the power I pi by 4? E to the power I pi by 4 is cos pi by 4 plus I sin pi by 4, and cos pi by 4 plus I sin pi by 4 is 1 plus I upon root 2. Now What is this particular figure? Modulus of Z3 minus Z1. Modulus of Z3 minus Z1 is the length of this diagonal, and modulus of Z2 minus Z1 is this. So if it is A, then it would become A root 2. So this upon this is equal to root 2. So root 2 1 plus I divided by root 2 is 1 plus I. So what is the final solution? Z3 minus Z1 is equal to Z2 minus Z1 plus I, and if we take this minus Z1 to the right, we get Z3 is equal to Z1 plus Z2 minus Z1 bracket 1 plus I. Similarly, if we rotate Z4, if we rotate this by angle of 90 degree, we can also say that okay, now let us rotate Z4 Z3 to by another angle of 45, but then it would be difficult because we have to give the answer in terms of Z1 Z2. So let us rotate Z2 by an angle of 93, and then as per the formula, the Z1 point would lie along this line, and because this length is same, it would match exactly here. So Z4 minus Z1 upon Z2 minus Z1 is equal to modulus of this, but this is these modulus are equal, and it is equal, and the angle is e to the power I pi by 2, that is cos pi by 2 plus I sin pi by 2, which would be equal to I. So again, by expanding, we can write that Z4 is equal to Z1 plus I multiplied by Z2 minus Z1. Our next topic is de Moivre's theorem, although it is rightly pronounced as de Moivre's theorem, but we will keep with Indian traditions and will say what most Indians say, that is de Moivre's theorem. So as per de Moivre's theorem, if theta 1, theta 2, theta 3 up to theta n are element of real number set, then cos theta 1 plus I sin theta 1 multiplied by cos theta 2 plus I sin theta 2 and so on multiplied by cos theta n plus I sin theta n is equal to cos of theta plus 1, theta 2, 3 plus theta 3 up to theta n plus I sin theta 1 plus theta 2 plus theta 3 plus up to theta n. This is the first statement of de Moivre's theorem. Now the second statement says that if we put if we take the case of theta 1 is equal to theta 2 is equal to theta 3 up to theta n, then this theorem reduces to cos if for a theta and element of r and n element of I, that is set of integers, cos theta plus I sin theta to the power n is equal to cos n theta plus I sin n theta. On the basis of these two theorems, we have derived some important results which I will present to you next. That if it is instead of this plus sign here, if we have cos theta minus I sin theta to the power n, then its value would be cos n theta minus I sin n theta for all n element of I. Then cos theta, then what is the value of sin theta minus I cos theta to the power n? If by simple manipulation you would come you would come to know that its value is equal to I to the power n cos n theta minus I sin theta, I sin n theta. Similarly, sin theta minus I cos theta to the power n would be equal to, if we take minus I common out of this this expression, then minus I to the power n cos n theta plus I sin n theta. Now another very important fact is whether cos theta plus I sin phi to the power n, is it equal to cos n theta plus I sin n phi? It should be n phi here, but it is not. For de Moivre's theorem to have any meaning, both the angle here theta and angle phi should be same. So this theorem holds only when cos theta plus I sin theta is being raised to the power n. The main use of de Moivre's theorem is in the finding roots of unity, say whether they are cube roots of unity, or especially in case of n nth roots of unity, de Moivre's theorem is found to be very useful. Now let us take a very simple example of de Moivre's theorem. In this example, value of xa is equal to given, that it is equal to cos pi by 4 to the power n plus I sin pi by 4 to the power n. Then we have to find the value of x1, x2, x3 up to infinity. Here it should not be xa but xn. So that x1 becomes cos pi by 4 plus I sin pi by 4, etc. Now, what is this multiplication? The multiplication we can simply write as here cos pi by 4 plus I sin pi by 4 multiplied by cos pi by 4 square plus I sin pi by 4 square plus cos pi by 4 cube plus I sin pi by 4 cube up to infinity. What does it mean? What does this expression evaluates to as per de Moivre's theorem? It is that this is equal to cos of pi by 4 plus pi by 4 square plus pi by 4 cube plus up to infinity plus I sin pi by 4 plus pi by 4 square plus pi by 4 cube. This is nothing but a geometric series. So it is equal to cos pi by 4 upon 1 minus pi by 4 and plus I sin pi by 4 upon 1 minus 1 upon 4. That is equal to cos pi by 3 plus I sin pi by 3, and it is equal to 1 plus I root 3 by 2, and which in this case is option 1. The first option is correct. See, when explaining a concept, we are giving very simple examples. But after we have explained all the concept, we will be giving you examples of the JEE Mains and Advanced Standard, because at this time our aim is just to explain the concept of say de Moivre's theorem or any other concept. So don't feel that we will not be testing you with really tough examples. Yes, they are those tough examples are on their way. Our next topic is cube roots of unity. The cube roots of unity means that if say z cube is equal to 1, what are the values of z? So far, when we were living in the realm of real numbers, we were saying that z is equal to only 1. But now with complex numbers coming into play, if z cube is equal to 1, it means that z cube z is equal to 1 to the power 1 minus 1 by 3. And how do we write 1 in the form of cos theta and sin theta? Using cos theta and sin theta is that it is cos 0 plus I sin 0, and if we add 2m pi in this, because we can no matter how many multiples of 2 pi we add, the answer value will remain same. So we will get cos 2 pi plus I sin 2m pi to the power 1 by 3. Here it should be cos 0 plus I sin 0. Then it would be 1 plus 0, that is 1 to the power 1 by 3. Now, what is the value of this? The value of this is cos, then what is the value of z? Z as per the de Moivre's theorem. We have already told you that we would be using de Moivre's theorem for calculating the roots of unity, whether be it the cube roots or nth roots of unity. That is where we normally use it. So if we expand this expression, then what do we get? We get this is equal to cos 2m pi upon 3 plus I sin 2m pi upon 3, and for what values of m? It would be 0, 1, 2, because we are calculating 3 roots, so we should have 3 values. But what if we put m is equal to 3? If we put m is equal to 3, then we get cos 2 pi plus I sin 2 pi, which is nothing but cos 0 plus I sin 0, that is 1, 0. So after 2, the value would start repeating. That if we put m is equal to 4, then we will get this value. If m is equal to 5, this value. So we can get only 3 unique solutions by putting m is equal to 0, 1 and 2. Now if we expand this, then what do we get? For 0 we get obviously 1, and for as m is equal to 1, we get cos 2 pi by 3 plus I sin 2 pi by 3, that is minus 1 by 2 plus I root 3 by 2. Now we represent this number as omega. Now if this is one of the complex roots of the equation, then what would be the other root? Obviously it would be minus 1 by 2 minus I root 3 by 2. That would be the conjugate of this particular number, because we know that complex roots always occur in conjugate pairs. But we can also calculate this root by putting m is equal to 2, and we would see that what is that its value come to be as we had predicted earlier. See. So it is cos 4 pi by 3, that is pi plus pi by 3 plus I sin pi plus pi by 3. So it is minus 1 by 2 minus I root 3 by 2. We denote this as omega square, that if we square this value of this, then we will get this value. Now what this thing you can also check by squaring this number, and you will see that this comes to be the same as this. It doesn't look likely, but believe me, it does, and you can give it a try. Now how do we represent these two roots and the unit value on an argand plane? 1, 0 is very easy to represent. It is here, and the minus 1 by 2 root 3 by 2, it would be here, and we know that argument of this particular is 2 pi by 3. So 2 pi by 3 is this angle. It has been shown as this, but it is actually 2 pi by 3 is this angle. Now angle between this and this is also 2 pi by 3, and this is minus 2 pi by 3 here. So these are the three roots. This is the argand. This is the representation of cube roots of unity on argand plane. Now there are some important things I want you to remember with regards to cube root of unity. One, that modulus of all of them is equal to 1. Obviously modulus of 1 is 1, modulus of omega is 1, modulus of omega square is equal to also equal to 1. You can also check it, and it has to be obvious because they are represented by cos 2m pi plus by 3 plus I sin 2 pi m pi by 3 for different values of this, and for all values of m the modulus of this particular thing is equal to 1. And thing is that omega cube would be equal to 1, because omega is root of this equation z cube is equal to 1. So if we put omega here, we get omega cube minus 1 is equal to 0, implies that omega cube is equal to 1, and omega square is also a root of this equation, to omega to the power 6 is also equal to 1. What does it mean? That omega to the power 6 can also be written as omega cube whole square. Omega cube, now we have already seen it is equal to 1. So omega square, omega to the power 6 is also equal to 1. Another important thing to note is that all the cube roots of unity differ by an angle of 2 pi by 3. 2 pi by 3 here, 2 pi by 3 here, and 2 pi by 3 here. What if we were calculating the cube, the fourth roots of unity? Then they would differ by 2 pi by 4 with each. So they would be 0, I minus 1, I minus 1, and minus I, and the angle between them would be 2 pi by 4, because then in that case this instead of 3 we will get 4. So it would be, if we are calculating the fourth roots of unity, then z to the power 4 would be equal to 1, and accordingly the value of z would be 2m pi by 4 plus I sine 2m pi by 4 for m is equal to 0, 1, 2, 3. When we put these values in this, for m is equal to 0, obviously it is 1, 0. For other values, we will get the values as pi, minus 1 and minus pi. Now some important results. What have we observed here about this, that these two numbers, they are it's not only the two non-real solutions of cube roots of unity. Not only that, one is square of the other. This is square of this and this is square of this. Why? Because if we do omega square whole square, then what do we get? We get omega to the power 4, that is omega cube multiplied by omega, and omega cube is equal to 1, so we get omega. So square of omega square is equal to omega. So both the non-real roots of unity, they are square of each other, and second, that they are bound to be conjugate to of each other, because complex roots occur only in pair. So we can very safely say that omega bar is equal to omega square, and omega bar whole square, what would be that? Omega square is equal to omega bar is equal to omega square, and it is omega to the power 4 is equal to omega. There are some other obvious results, like root of omega is equal to plus minus omega square, root of omega square is equal to plus minus omega. You can always check these results on your own. I am not explaining them here. Now, what is the modulus? We have already told that modulus of both these roots is equal to 1, because anyway they are the cube roots of unity, so their modulus has to be equal. And another reason their modulus is equal, because they come from by putting value of m as 1 and 2 in this equation, and for all values of m the modulus of this is equal to 1, that is cos square 2m pi by 3 plus sine square 2m pi by 3, which is equal to 1 for all values of m. Another very important result is that value of 1 plus omega square is equal to 0. So what is that? That is the sum of all the roots of the unity is equal to 0. Why is it so? Because z cube is equal to 1 and z cube minus 1 is equal to 0. So sum of the roots of this equation is bound to be 0, because the coefficient of z square is equal to 0. So 1 plus omega square, that is the sum of the roots of cube roots of unity, is equal to 0. Now some warm-up problems on cube roots of unity. In this case, we are supposed to prove that log of at the base 2 modulus 1 plus omega square plus omega cube minus 1 upon omega modulus close is equal to 1. Now what is here? Omega is not the cube root of unity, but it is the imaginary fifth root of unity. It is very important to mention imaginary, because omega can also be equal to 1. So the question is specifically specifying that omega is an imaginary fifth root of unity. Now in this case, what happens, that 1 plus omega square plus omega cube plus omega to the power 4. These are the 5 fifth roots of unity. Now their sum would be equal to 0. So sum of these 4 terms would be equal to minus omega to the power 4 here. And what is the value of 1 upon omega? Omega to the power 5 is equal to 1. So if we substitute here 1 with omega to the power 5, we get minus omega to the power 5, and sum of this is also equal to minus omega to the power 4. So what do we get? minus 2 omega to the power 4. Now what is the value of modulus of this number? It is equal to modulus of minus 2 multiplied by modulus of omega 4. Modulus of minus 2 is 2. And what is the value of modulus of omega 4? It would be 1, because modulus of omega is equal to 1, it being the cube fifth root of unity, one of the roots of unity. Therefore, it would be of the form of, say, cos m pi by 5 multiplied by 2m pi cos 2m pi by 5 plus I sin 2m pi by 5, where m is equal to 0 between 1 to 4. So for all those, for every value of m, the value of omega would be, modulus of omega would be 1. So this reduces to log 2 to the base 2, which would be equal to 1. See, it's a one line solution. It looked so bad here. Now let us take another example. Okay, in this example we are asked to find the sum of common roots of the equation. This and this may have so many roots, but this has only 3 roots. What are these 3 roots? To find those 3 roots, let us try to manipulate this thing, and we can say that this can be written as z cube plus 1 plus 2z, z plus 1. Like this, z cube plus 1 plus 2z, z plus 1. Now, if from both the sides we take z plus 1 common, what do we get? In this we will be left with z square minus z plus 1, and here we would be left with plus 2z. So, if we take z plus 1 common, we will get z plus 1 multiplied by z square minus z plus 1 plus 2z, that would be equal to z square plus z plus 1. So this is equal to z plus 1, z square plus z plus 1 is equal to 0. Now what are the roots of this? The roots of the solution of this is z is equal to minus 1, and this we know from the cube roots of unity that the roots of this equation are omega and omega square. So the roots of this cubic equation, z cube plus 2z square plus 2z plus 1 is equal to 0, are minus 1, omega and omega square, where omega and omega squares are the imaginary cube roots of unity. Now let us see which of these roots satisfy this. So to find whether the common roots of the equations. Now common roots of, if we put minus 1, then this is minus 1, this is also minus 1. So this is not satisfying. So but then whether omega and omega square are going to satisfy it? Yes, if they have any common roots, then both of them, one of them should satisfy this. Then omega and omega square are conjugate to each other, as we have seen earlier when studying the cube roots of unity. We can say that both omega and omega square will be satisfying this. So the common roots are omega and omega square. Then omega, what is the sum of omega, these common roots? It is omega plus omega square. But we know that 1 plus omega square is equal to how much? 0. So omega plus omega square, the value would be equal to minus 1. Now let us find nth roots of unity. We have already calculated the cube roots of unity. There what we had done, that z cube is equal to 1. Now since we have to find nth roots of unity, we have to say find z such that z to the power n is equal to 1. So z to the power n is equal to 1 means z to the z is equal to 1 to the power 1 upon n. And 1 in complex number notation we can always write as cos 0 plus I sin 0. This we can also write 2n pi. We can always add 2n pi here as well as here. So this equation becomes cos 2m pi plus I sin 2m pi to the power 1 upon n. Now using de Moivre's theorems, we have already said that De Moivre's theorem's main use is in finding the roots of unity. So what is the value of this as per De Moivre's theorems? It would be equal to cos 2m pi upon n plus I sin 2m pi upon n. And what is the value of m? M can be 0, 1, 2, 3. So here m was anyway integer. So if we put the values of m is equal to 0, 1, 2, 3 up to n minus 1, we will get n distinct roots. What if we put m is equal to n? Then this n cancels out. This is 2 pi plus I sin 2 pi, and we get the original result, that is cos 0 plus I sin 0, which we had when we put the value of m is equal to 0. Now these roots start repeating themselves after we put m is equal to n minus 1. After that, when we put m is equal to n plus 1, we again start getting the same roots as we would get when we put 0, 1, 2, 3. So that is the rationale behind putting m is equal to 0, 1, 2, 3 up to n minus 1. Now if we put m is equal to 0, z1 is equal to 1. If we put m is equal to 1, here we get z2 is equal to cos 2 pi by n upon plus I sin 2 pi by n. This is nothing but, as per Euler's formula, this is e to the power I 2 pi by n. If we say it is alpha, then what is the value of z3? M is equal to 2, we get z3 is equal to cos 4 by n plus I sin 4 pi by n is equal to e to the power I 4 pi by n is equal to alpha square. Now it is obvious from these two expressions that this root is square of this. As we had seen in case of cube roots of unity, the two roots were square of each other. But is this root conjugate of this? No, it is not the conjugate of this one. See, in case of cube roots of unity, there were only 3 roots, and here it is not. I will tell you what alpha is conjugate of. There has to be a conjugate of alpha as root of one of the n roots of unity, but which one it is, that I will tell you later. But it is not the conjugate of alpha square, as we had seen in case of cube roots of unity. Now for m is equal to, say, up to n minus 1, what is the value? 2n minus 1 upon 5 upon n, and plus I sin 2n minus pi divided by n. So this is alpha to the power n minus 1. Now this alpha to the power n minus 1, if we calculate for a particular value of n, will be the cube, this conjugate of alpha, and alpha square conjugate would be alpha to the power n minus 2. You can check this thing results by taking a particular case, and by thinking about it also you would realize that this would be the situation. Now some important results. I am not proving these results, I am just mentioning these results as of now. So if 1 alpha 2 and alpha n minus 1 are the nth roots of unity, then the value of this expression is equal to 0 if p is not an integral multiple of n, is equal to n if p is an integral multiple of n. We will try to give examples where these properties will be used, but as of now we are just mentioning it. Alpha 1 multiplied by 1 minus alpha 2 up to 1 minus alpha n minus 1 is equal to 0 if n is even, and it is 1 if n is odd. Here this is not a type of 1, this is 1 plus alpha 1. Now in case of all of them with negative sign, 1 minus alpha 1, 1 minus alpha 2 up to 1 minus alpha n minus 1, this product will be equal to n. You can try to prove these results on your own. That would enhance your understanding. Now let us take a very beautiful example which will explain the concept of n nth roots of unity. In this case, we are taking the value when n is equal to 8. So we have got 9 roots of unity. Alpha up to 1, alpha 1, alpha 2 up to alpha 8. And we have been asked to find the value of modulus of 2 minus alpha 1, 2 minus alpha 2, 2 minus alpha 5 and alpha 7. The alpha 2, 4, 6 and 8 are missing. Now, in this type of question, the first thing you have to think where to start from. Can you just expand this and try to then manipulate? It would be very difficult, and here it is good to be a bit lazy. That at least this cannot be the proper way. There's so much calculation. J is not the test of your calculation speed. It is the test of testing your capabilities to think, to be intuitive in some cases, as in this case, in this problem. Now, how will we get this kind of expressions? One thing we know that alpha 1 is the conjugate of alpha 2, alpha 2 is the conjugate of alpha 7. So that is okay, we'll keep it in mind. As of now, we cannot apply this thing here. Okay, what then where to start? Now let us go to the basic definition. Since these are the 9 roots of unity, so let the equation was z to the power 9 minus 1 is equal to, then what is the value of z to the power 9 minus 1? It would be equal to z minus 1 multiplied by z minus alpha 1, because these are the roots of this equation. So let us try and see if we can get some good results here. So if we do this x minus 1 multiplied by x minus alpha 1, x minus alpha 2 up to, here it is up to x minus 8, then the value is x to the power n minus 1. Because even if we check it by expanding it, we will see that sum of the roots is 0, 1 plus alpha 1 plus alpha 2 up to 8 is 0, taken 2 at a time is 0, so only the product would be remaining. So we can always check and find that this is a correct equality, and we have to keep this in mind, that x to the power n minus 1 is always equal to x minus 1, x minus alpha 1 all the way up to x minus alpha to the power n minus 1, where these are the cube roots of n nth roots of unity. Now, another thing we know that if these alpha 2 is alpha 1 square, alpha 8 is equal to alpha cube, but at this stage we don't think it can help us in any way. Now, if we put in this equation x is equal to 2, then what do we get? 2 minus 1 is equal to 1, 2 minus alpha 1. So that is something which is required here. So let us put x is equal to 2 here. So we get 2 minus alpha 1, 2 minus alpha 2 dot 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 up to 2 minus alpha 8 into 2 to the power 9 minus 1. 2 minus 1 is equal to 1. So we have not written that here. Now we know that 2 minus alpha 2 would be equal to 2 minus alpha 7. 2 minus alpha 1 and 2 minus alpha 7, they would be equal to each other. So this, if we eliminate the even points, because 2 minus alpha 2 will be replaced with 2 minus alpha 7, then because here in this expression 2 minus alpha 2, 2 minus alpha 4, 6 and 8 are not here. So alpha 8 also we will change accordingly. So what do we get? Alpha 2 minus alpha 8 would be equal to 2 minus alpha 1. So that way what do we get? We get 2 minus alpha 1, 2 minus alpha 3, 2 minus alpha 5, 2 minus alpha 7 whole square. Because other terms are also equal to this product, so we get the whole square of this is equal to 2 to the power n minus 1. As these are a conjugate to each other, so we know that this is 2 minus alpha 1 is equal modulus of this is equal to modulus of 2 minus alpha 8. Now, so similarly we can write all these things and we get to this, that this product modulus of this would be root of 2 to the power n minus 1 is equal to root of 511. Please see that we had been saying that alpha 1, alpha 8 are conjugate to each other. But if alpha 1 and alpha 8 are conjugate to each other, then 2 minus alpha 1 and 2 minus alpha 8 will also be conjugate to each other. Now, you can try it by putting alpha 1 as a plus ib and alpha 8 as a minus ib, and you would realize that these two numbers will come out to be conjugate to each other. It is obvious, you can just give it a try. With this we will conclude this lecture, and in next lecture we will do some warm-up problems, some really basic problems on the concept which we have learned. When I say basic, I mean basic with reference to JEE, not with reference to class 11, 12. So some really useful problems, but not very complex problem. Some of them are good for even JEE mains examination. But first we have to learn the fundamentals, concepts and tricks from these problems. Then we will do some really complex problems. Our stress is to get the theory out of way first. Then when we are teaching theory, we don't go into too many examples and too many complicated examples, because then rather than telling you the basic concepts, we get entangled in the various tricks involved in the question. So those questions we will also do in subsequent lectures, but as of now we have explained the concept with really simple problems. So with this I conclude this lecture. Thank you.